Welcome back to our series on statistical mechanics. Today we are going to discuss one of the important topics in statistical mechanics called ensembles. If you remember, in one of our previous episodes, we introduced the terms or discussed the terms microstate and macrostate. There we discuss the connection between the two terms macrostate and the microstate. From that episode we know that every macrostate is having certain constant parameters. For example, NVT, number of particles, volume, temperature. But with the same set of parameters being kept constant, there could be certain other variations in the system which could lead into a distinguishability between different instance in which through which the macrostate passes, and we represented or we called such kind of variations by the term microstate. For example, if the energy of the system in which the N, V and the T are being constant, if the energy is getting varied, then one of the microstate in that macrostate, which for example E1, E1 with NVT constant and the energy E1, it can be called as one of the microstate in this macrostate. And after some time, the same macrostate could be find in a microstate with energy E2. So that was that was an extension of our discussion on the microstate and the macrostate, which you can go back to the earlier episode and make yourself reminded. So here we know that every macrostate at particular instant is having a particular microstate. Okay. But when it comes to statistical mechanics, its evolution or its development has to happen in a theoretical manner. For those purposes, we introduce this concept called the ensembles. There, what happens is that we assume that all the microstates with which this macrostate can be represented are present at the same instant. That means, say at time t1, all the microstates which are possible with the macrostate are simultaneously present in the macrostate. So that is exactly what the term ensemble means. So telling it more precisely, the term ensemble can be defined like this. So it is a collection of similar but independent non-interacting systems. Let me write it down so that to emphasize, collection of similar but non-interacting systems. Now the term systems in various literatures you will find in different words. Many times one of the terms with which the term systems could be expressed is by the term elements. So therefore, the term elements, with the terms I can tell that these systems or the so called members which are otherwise called the elements are defining this particular macrostate. So a macrostate will have different elements at the same instant of time. So, this idea was originally proposed by Gibbs. Gibbs originally proposed this concept of ensembles. If you remember, when we were discussing the history of statistical mechanics, I told you about the importance of Gibbs, the contribution of Gibbs in the development of statistical mechanics, and the concept of the ensembles forms basically the backbone of the theoretical development of the statistical mechanics. There is another way of talking about it, which the Gibbs himself talk about, which is called the system of systems. System of systems, right? The concept of ensemble actually replace a time average system with a time independent system, which was very much essential for the theoretical calculations, which will get which you yourself will also get a flavor in our later episodes which are planning on this. So, basically, as I told you, at time t1 we were having a particular microstate, at time t2 we were having another microstate, time t3 we were having a different microstate. So, if we need to find out the behavior of the statistical system, one thing we needed to do was to find out its time averaging. Now, what is the advantage? We are taking the time out of this statistical development, because we are assuming that at the same instant of time itself, the concept of ensemble accommodates all the microstates which are possible in the macrostates. Now, let me explain it further by taking one of the major ensembles, which we call as the canonical ensemble. This is the most significant or most widely used among the ensembles. As Gibbs writes in his paper, there are innumerous number of ensembles possible for a statistical system, but there are three major kinds of ensembles, and canonical ensemble is the most important among all those three. In the canonical ensemble, we assume that the parameters number of particles, volume of the system and the temperature are constant. So, this is the major assumption for the canonical ensemble, which means what? Which means that the parameter which defines our macro state for a canonical ensemble system is the NVT, right. So, therefore, what is the parameter which you could assume that it could be changing in this ensemble is the energy of the system. Energy of the system is allowed to vary in this ensemble, and therefore, we define it by EI. Let us try to represent this canonical ensemble system by a diagram, which is pretty important for the full understanding of the system. So, there we should assume that since we need to have the system with temperature as a constant, which means that we should be thermally insulating our whole box or the whole system in which this ensemble is existing as thermally insulated, which I will represent it like this. Right. So, it is totally thermally insulated, wall, and we can assume that within this box the system is divided into different microstates, right? That was our major assumption. So, let us divide this system into different microstates. So, inside the box I can represent as NVT, and so on and so forth. NVT, and there the variation is in the EI. So, this can be E1, this can be E2, E3, E4, E5, E6 and so on and so forth, right. So, if I need to make sure that all these microstates are at the same temperature, one of the things which the physics people assume is that this has to exist in something called the heat bath. So, heat bath is an arrangement in which the temperature is same throughout the system. So, I can so the system is assumed to be existing in a heat bath. Okay, so it is thermally insulated, but within this system it is totally in a heat bath. And what is the speciality of these walls? The walls which are separating the microstate. So, that has to be diathermic walls, right. The walls are to be diathermic, and then I need the number of particles to remain constant, and therefore, it has to be, that means there should not be any transfer of particles between the walls. So, therefore, I can tell that it is impermeable, and the volume has to remain constant. Therefore, I can I need to assume that the walls separating the microstate has to be rigid. So, what are the conditions? It has to be totally separated by a thermally insulated jacket, and it has to exist in a heat bath, and then the walls separating the microstates or the elements of the ensembles are to be diathermic, and it has to be impermeable and rigid. So, as I told you, so this is how we define a canonical ensemble. Most of the situations which we will be dealing in statistical mechanics in the real life belongs to this class of ensembles. Next one is the microcanonical ensemble. So, the microcanonical ensemble gets its importance because of its simplicity. Simplicity in terms of the kind of hypothesis which we can bring into the microcanonical ensemble. But one should always be careful. In the real world, there is no system which can be equated to a microcanonical ensemble. So, this is totally a theoretical proposition, the microcanonical ensemble. So, what is it? So, here in the microcanonical ensemble, the number of particles n, the volume V, and the energy of the system NVE is assumed to be constant. Here you can always contrast with the kind of ensemble which we presented earlier, in which the N, V and the T were kept constant. As I told you, this is totally a theoretical proposition, because in a system it is in a real world system, it is almost impossible to keep energy constant for a system. So, how do we represent the microcanonical ensemble? So, you have already the experience of drawing the diagram for canonical ensemble. based on those experiences, we know that here it has to have the n constant, which means that it has to be impermeable walls. V has to remain constant, which means the walls has to be rigid, and the energy needs to be constant. Energy needs to be constant means we have to assume something called the adiabatic walls, right. So, there that I can represent it like this. Right. So, there NVE so this is the kind of system which we will have. So, I can represent the NVE and so on and so forth for all the elements in the ensemble system. Now, the question could be, which could arise in your mind, could be, so then what is that which is changing, right. Here the safest way in which we can assume something which changes is the internal energy of the system, right, which we normally represent it by epsilon I. So, a system can have the same complete energy, but the system can be arranged in various energy levels, so that the internally its energy levels are different, and therefore, internally its EI can be assumed to be different at different instants of time. So, that is how all these microstates are being distinguished. Otherwise, for the macro state NVE are kept constant, right. And I already told you the conditions. The walls has to be adiabatic, it has to be rigid and impermeable walls, right. So, now the next kind of ensemble is the grand canonical ensemble. This kind of ensemble is mainly applicable in the chemical reactions. We know that what happens in chemical reactions, there will be two or more reactants, and you will get one or more products. So, there one of the consequences is the number of particles of the system is going to change, right. So, therefore, here in general the macro state of the grand canonical ensemble, we define that the mu V T is assumed to be constant. What is mu? If you remember, in one of the episodes we already represented that mu is called the chemical potential of the system. Mu is the chemical potential of the system. So, here when we are trying to represent it, the diagram, what are the assumptions which we should be making, right. There now we are allowing the number of particles to change, but the chemical potential is constant, but the number of particles to change, but which means that I have to assume the permeable walls, and the temperature is kept constant, which means that I have to assume diathermic walls, and the V is constant, therefore, it has to be rigid. So, let us try to draw that. So, the T has to remain constant, which naturally tells me that I have to be thermally insulated from the external atmospheres, right. And so on and so forth. Mu Vt kept constant, rigid walls, because the volume is one of the constants here, and the temperature is kept constant, which means that it has to be diathermic walls. And the number of particles do change, which means that my walls has to be permeable. These are the assumptions on which the grand canonical ensemble is constructed. Therefore, there are three main kinds of ensembles. One is the microcanonical ensemble, which is mainly applicable for the theoretical assumptions, and then there is the canonical ensemble, which is mainly applicable for all the real world cases, and then there is the grand canonical ensemble, which is mainly applicable for the chemical reactions. So, this is how so the concept of ensembles is really important for the theoretical evaluation of the development of the statistical mechanics. Now, we need to find out more concepts which could be helpful for the evolution of ensembles. So, with the concept of ensembles, we found out a better connection between the microstate and the macrostate. Now, we need to make a framework which will be applicable for the theoretical development of the statistical mechanics through the evolution of the ensembles, which we will try to do in one of the coming episodes. Thank you.